Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my second lecture on the concept of block diagram reduction technique. In my previous lecture on block diagram reduction technique, I have discussed various rules that need to be implemented for block diagram reduction technique. I also discussed some of the tutorials based on this block diagram reduction technique. So in today's lecture, we are going to continue to solve some more tutorials based on block diagram reduction technique. So before we solve some more tutorials, let me quickly recap the rules that I have discussed in my previous lecture for block diagram reduction technique. The first rule, when two blocks are in cascade G1, G2, I can replace by the single block by multiplying the gains of the two blocks. When blocks are in parallel, rule number 2, depending on the polarity, I can replace that by a single block. If it is positive, then you will get G1 plus G2. If it is negative, it is G1 minus G2. Rule number 3, eliminating feedback loop. So G is the gain in forward path, H is the gain in reverse path. So depending upon the feedback, so if it is negative feedback, then I will get G by 1 plus G into H. If it is positive feedback, then I will get G by 1 minus G into H. So remember that I told you that while implementing these rules, the expression for output C of S should not change. Associative law. So when I have two summing points adjacent to each other, I can interchange these two summing points. Thereby the expression also will remain same. So rule number 5. I need to shift my takeoff point before block G. So when I shift my takeoff point before block G, I need to multiply the takeoff point by the gain of that block G. It's rule number 6. If I want to shift my takeoff point after the block G, so I need to multiply my takeoff point by 1 by G. So rule number 7, shifting summing point before block. So when I shift my summing point before a block, I need to multiply by 1 by G. And 8th one, shifting summing point after the block. So if I want to shift my summing point after the block, I need to multiply with the gain value of the block, that is G. And lastly, when my summing point has more than two inputs, I can split my given summing point into two summing points, so that the expression will not change and remain same. So these are the rules that are already discussed in my previous lecture. Let us move forward to solving some more tutorials based on block diagram reduction technique. So here we need to find the overall transfer function. So in the first step, I will shift my takeoff point before the block G2. So according to rule number 5, if I want to shift my takeoff point before the block G2, I need to multiply the takeoff point by G. In place of G, I have here G2. So after shifting the takeoff point from here to here, I need to multiply the takeoff point by the block gain G2. So in the next step, these two are in cascade, G2 and G3. So that will become G2 into G3. In the next step, these two blocks are in parallel. So that will give me G4 plus G2 into G3. So I'm replacing that a single block. In the next step, I am shifting this summing point before the block G1. So according to my rule number 7, if I need to shift my summing point before the block, I need to multiply by 1 by G. Okay, here since the gain value is G1, I need to multiply by 1 by G1. So here I have multiplied by 1 by G1. These two are in cascade. These two also are in cascade. So we can combine these two, and if I combine these two, this will become H2 by G1. If I combine these two, that will become H1 into G2. Okay, you can do that in this step. So since I have two summing points adjacent to each other, okay, so according to associative law, I can interchange these two summing points. So why I am interchanging the summing points? In order to separate these two loops. This is the first loop. One, let me clearly draw so that you can understand. Okay. So this is one loop, and this is the second loop. Okay. So in order to separate these two loops, I am interchanging my summing point. Please observe carefully. After I interchange my summing points, you can see clearly that the two feedback paths have been separated. Okay, so it will be easy for me to further reduce my block diagram. Okay, so in the next step, these two are in cascade. That will give me H2 by G1, and these two will give me H1 G2. So next will be eliminating feedback loop, that is nothing but G by 1 plus G into H. In place of G, I have G1. In place of H, I have G2 into H1. So upon applying the formula, that will give me G1 divided by 1 plus G1 G2 into H1. So these two blocks are in cascade. So I'll just multiply these two blocks. That will give me G1 into G2 G3 plus G4 divided by 1 plus G1 G2 H1. So obviously this is a feedback loop. Applying the formula, you will get this on simplification. That is G1 into G2 G3 plus G4 divided by 1 plus G1 G2 H1 plus H2 into G2 G3 plus G4. Again here feedback path value is 1. This is in place of G. So applying the same formula, that will give me my transfer function C of S by R of S as G1 into G2 G3 plus G4 divided by 1 plus G1 G2 H1 plus G2 G3 H2 plus G4 H2 plus G1 G2 G3 plus G1 G4. So upon LCM you will get the final answer. So here I need to find my overall transfer function. So here I need to separate my feedback loops as the first case. Let me show you the feedback loops that are present. So first feedback loop here, H2 H1, it goes to the first summing point. So first summing point has feedback H1 H2. Okay, so when I observe this summing point, so if I change the color so that you can clearly understand, so this is H2 and it is going to my second summing point. So this summing point has a feedback loop gain H2, and third summing point, that is this summing point, if I observe carefully, the gain is H2 H1, the pink line is going to this, so this will have H1 H2. Okay, so as first step, these three feedback loops I'll try to rearrange. Okay, so it will be easy for me to reduce my block diagram further in further steps. So as the first step, I need to rearrange the feedback loops as I told you earlier. So this first summing point will have the gain H1 H2 as we have seen. The second summing point will have the gain feedback gain as H2. Third summing point will have feedback gain as H1, H2. Okay, so the remaining steps will become very easy for us to solve, isn't it? So here, since the summing point will have 3 inputs, that is why I need to split my summing point according to rule number 9. So single summing point I have split it into 2 summing points. The next step, these 2 blocks are in parallel, so it becomes G1 plus G2. Then these forward gain is G4, feedback gain is H1, H2. So eliminating feedback loop, we get G4 by 1 plus G4 into H1 into H2. These 2 are in cascade, so that will give me G3 G4 divided by 1 plus G4 H1 H2. Eliminating feedback loop, we have G in place of G3 G4 by 1 plus G4 H1 H2. In place of H I have H2. Applying the formula, since it is negative feedback, I'll get positive in the denominator. So on solving and simplifying, I get G3 G4 by 1 plus G4 H1 H2 plus G3 G4 H2. These 2 blocks are in cascade. You just multiply, that will give me G1 plus G2 into G3 G4 by 1 plus G4 H1 H2 plus G3 G4 H2. As the last step, eliminating feedback. So on taking the LCM and solving will give me the transfer function as G1 plus G2 into G3 G4 by 1 plus G3 G4 H2 plus G4 H1 H2 plus G1 G3 G4 H1 H2 plus G2 G3 G4 H1 H2. So here I need to find my overall transfer function using block diagram reduction technique. Here I have my input and output adjacent to each other. So I need to redraw such that my input is to one extreme and output is to my another extreme. So I am redrawing the given block diagram. So here I have R1. So from R1 I have one summing point. From summing point I have G3. From G3 I am having one more summing point. From this summing point I have the gain G8. From G8 I have G5 and G2 in cascade. And from G2 I have the block G1. From G1 I am getting my output C of S. Okay, so let me see the remaining loops also. Okay, so from this I have a block. So from this, that is before G5, in between G8 and G5, that is this one. I am getting a block G7. From G7 it is going to a summing point. Okay, so again in between G2 and G1, so that is this point, I am getting a gain of G4 and that is going to the same summing point. Okay, next the output of the summing point is going to a block G6 and from there it is going to a summing point. This is this summing point with a negative feedback. Okay, and one more feedback is left, that is from G1 the signal as negative feedback is going to my first summing point. So from G1 my feedback loop is going to my first summing point as negative feedback. So here I have redrawn. Mind you, I have not changed the block diagram, but rather I have redrawn my given block diagram in a suitable manner so that it will be easy for me to solve the given block diagram. So here I have two feedback loops. Let me show you first. So this is G7, G6, one feedback loop. The second feedback loop is G4, G6. So two feedback loops are having one common summing point. So first I will separate these two feedback loops and rearrange in a manner so that it be easy for me. So here I have G7, G6, and here I have G4, G6. So you can, in the previous, you can see in one feedback loop you get gain G7, G6. In another feedback loop you get G4, G6. So the next step will be this eliminating feedback. In place of G I have G8, in place of H I have G7, G6. That will give me G8 by 1 plus G8, G7, G6. These two blocks are in cascade. So that will give me G5, G2, G8 by 1 plus G8, G7, G6. Again, eliminating feedback loop. On simplification, that will give me G5, G8, G2 divided by 1 plus G8, G7, G6 plus G8, G2, G5, G4, G6. These three blocks are in cascade. So the numerator will get multiplied by G1 into G3. So the feedback gain value is 1. So therefore on simplification will give me my required transfer function as G1, G2, G3, G5, G8 by 1 plus G8, G7, G6 plus G8, G2, G5, G4, G6 plus G1, G2, G3, G5, G8. So here we need to find the transfer function in the next sum, C of S by R1 of S. So observe carefully that here I have two inputs, R1 and R2. Since I do not need R2, here I assume my R2 is 0. So if R2 is 0, then there is no necessity of drawing this input R2 as well as this summing point. I can totally eliminate this since it is 0. Next, I will shift my takeoff point after the block G3. So according to rule, after I shift, I need to multiply by 1 by G. So in place of G, I have G3. So I will multiply the takeoff point by 1 by G3. So eliminating feedback loop, in place of G, I have G3. In place of H, I have H2. And also these two blocks are in cascade. That will give me H3 by G3. So here I have H3 by G3. Here I have G3 by 1 plus G3 into H2. So these two blocks are in cascade. So numerator I will have G2 G3 by 1 plus G3 H2. So eliminating feedback, this is G and this is H. You know the formula since it is negative feedback. On simplification, we'll get G2 G3 by 1 plus G3 H2 plus G2 H3. These two blocks are in cascade. So numerator I'll get G1 G2 G3 by 1 plus G3 H2 plus G2 H3. As the last step, we are eliminating the feedback. So this is in place of G, this is we have in place of H. So that will give me my transfer function as G1 G2 G3 by 1 plus G3 H2 plus G2 H3 plus G1 G2 G3 into H1. So this concludes my video lecture on the concept of block diagram reduction technique. So we have seen many rules that need to be implemented in block diagram. We also solved many tutorials based on the rules that we have discussed in block diagram. So in the next lecture, we are going to see the concept of signal flow graph. Thank you.